So again, grids are designed to transmit only X-rays traveling in a straight path, or a straight-ish path, from the X-ray tube through the radiolucent material, and the scatter is absorbed on the radiopaque grid strip. So we're going to refer back to the graphic or the image, and it's posted throughout the PowerPoint, and we'll look at this over and over again. So what you're looking at here is we've got primary beam, we've got remnant beam. So these are your image forming X-rays. Primary beam is the beam that's unattenuated before it reaches the patient. So it goes through the patient and you undergo all the interactions. So you get Thomson interaction, you get Compton interaction, you get no interaction with transmission, and you get photoelectric absorption inside of the patient. So what's left down here are your transmission, your scattered photons, and the scattered photons could be Thomson, could be Compton, either one. So what you're looking at in the grid are the dark lines represent the grid strips, and they are made of lead. So it's radiopaque material. Lead is very dense. It's hard to see through via X-ray. So those are your grid strips. And the interspace material here could be made of a number of different things. It could be plastic. It could be actually paper. Some grid strips use a less radiopaque material that's still radiopaque. What I mean by that is sometimes your manufacturers, instead of using something that's really radiolucent, they'll use something that is less radiolucent. Less radiopaque than the lead strips. So what you've got in some of your grids is the interspace material, and that's this gap in here, is instead of paper, it is aluminum, actually. So it absorbs more X-rays, but the reason that they use the aluminum is because the aluminum, being a more radiopaque material, makes the grid strip stand out less. So interspace material, grid strip, and that is your grid. So the effectiveness of grid, we've got a couple of different measures of effectiveness of grid. And when we talk about effectiveness, we're talking about the effectiveness of the grid to absorb scatter radiation. So we've got two different measures. Those are grid ratio and grid frequency. The more significant of those two is grid ratio. And grid ratio is it's a measure of the height of the lead, the grid strip, the lead strip, to the thickness of the interspace material. All right, so grid ratio is calculated as, if you look on page 195, you see grid ratio in the box closest to the bottom on the right hand side. So this grid ratio is the height of the lead strip divided by the distance in between them. You're going to have a tendency on a test to want to make grid ratio the height of the grid strip divided by the thickness of the strip. The thickness of the strip is important because it's more lead. The thicker the strip is, the fatter it is, the more lead you have there. But the grid ratio is the height of the strip, the grid strip divided by the distance in between them. That's the calculation of grid ratio. So the effectiveness of the grid is determined by a number of different things. So the height of the grid strip, that is the taller or the thicker the grid, going back to the graphic, the thicker the grid is this way, then the longer these distances are in between the grid strips. So if you can imagine drawing this grid much further down, and you're looking at the different interactions inside of the grid, the further down this goes, the harder it would be for some of these photons to travel all the way through the grid. Like this one, well, let's say we take this one right here. If we were to take this grid and we were to cut it down in half, then this grid strip, or this scattered photon that's ending right on the end of this grid strip would make it through the grid. So the taller the grid and the longer these canals are for the scattered photons to go through, the more vertical that they have to be and the less scattered that they would have to be in order to make it through the grid strip. So the height of the grid strip is very important. The thickness of the strip is also important, because if it's paper thin, like a foil type thickness of lead, then even though it's still lead, the chances of a scattered photon getting through it, a high energy scattered photon getting through it, is more likely. So we just came through technique and thickness, and tissue thickness, and how to adjust your technique for the tissue thickness. So as patient thickness increased, the patient absorbs more absorbs more radiation of any type, right? We create more scatter radiation, but more of that scatter radiation is absorbed inside of the patient because of more possible interactions inside of the patient. Same thing happens with the grid strip. The thicker the grid strip is, the fatter the grid strip is, the more it's going to absorb. So the thickness of the strip is important, but it's still lead, so it's going to absorb almost all of the low energy photons, even if it's very thin. So height of the grid strip is very important. Width of the space in between is extremely important as well. So going back to this, if we were to take, even if we were to cut this grid in half so that this photon would make it through, if we decrease the distance in between the grid strips, then again we would filter out this X-ray photon or this X-ray photon. So it's not just important to have the height of the strip and the thickness of the strip to absorb them as well, but also the number of grid strips, or how close the grid strips are packed together, increases the effectiveness of the grid. So the height of the strip, thickness of the strip, very important, but also the width in between, or the narrowness, actually. So what we have with a thick grid is that we've got a longer hallway. And the reason I put this in here is because I sometimes tell a story of my brother and I when we were kids. We used to have kind of like Nerf guns, only they were not Nerf guns where they would repeat like what Nerf guns do now. But they were these hard plastic darts with a suction cup on the end of them. And in the house I grew up in, we had a long hallway. This house was constructed in the 50s before open floor plans existed. So we had a long hallway, and we would have wars with these dart guns. And if one of us was taking cover in my mom's room and one of us was taking cover in our room behind the door, the hallway was, I would say, probably 30 feet long. And in order to get the dart to go all the way from one door to the other, your aim had to be pretty accurate, as opposed to if one of us advanced on the other and we snuck into my sister's room, which was about halfway down the hallway, it was easier to get a shot through the other person's doorway. So the longer the hallway, the more vertical, or the more accurate, or more parallel to the lead strips that the X-ray photon has to be in order to make it through. So it's going to absorb a lot of scatter radiation. Anything that's not going parallel with that long hallway is going to be absorbed. Same thing with the space in between. The reason it was hard to get a dart from one end of the hallway to the other was because it was not only long, but it was thin. So your aim had to be pretty accurate. If we thinned out that hallway even more, how much more so would you have to be accurate to get that dart from one end of the hallway to the opposite? So what we're looking at here is if this grid was twice as tall, these photons would have even a harder time getting through them. Or if the hallways or the interspace material in this case were half as wide, then how much more difficult would it be to get the X-ray photon through them? So those are the two main measures of grid effectiveness, is the height of the strip and the width of the interspace material. And that is why we calculate our grid ratio as those two things. So we got the height of the grid strip divided by the distance in between them. There's a couple of different ways we can get to an increase in grid ratio, and those are the two ways. If we have a grid and we double the height of the grid, then we double the efficiency of the grid. We double the efficiency of the grid and we double the grid ratio. If we add an extra strip in between each one of these, then we double the number of strips, and we effectively double the grid ratio again. So grid ratio, the higher the grid ratio expressed in numbers, like if we have a 5-to-1 grid ratio that we're comparing to an 8-to-1 grid ratio, the higher that first number, the more effective the grid, the more lead there is in the grid, the more cleanup there is in the grid. So higher ratio grid cleans up more scatter radiation than a low ratio grid. It absorbs more scatter. It absorbs more of all types of scatter, or all types of radiation, but certainly all types of scatter. Since we've got grid strips that are standing on end, if we have a unattenuated penetrated beam photon that strikes right here, it's going to absorb that photon. So it'll absorb primary, or not primary, but unscattered photons as well as scattered photons. So it's all secondary, but it absorbs unscattered photons as well as scattered photons. But it absorbs proportionally more of the scattered photons than what it does the unattenuated photons. So it lightens the exposure to the image receptor. It reduces the exposure to the image receptor. So if you were to set a technique, say you're shooting a portable KUB, you shoot a portable KUB without a grid, and you got a good technique. Let's say you got a good technique and you used maybe 80 kVp at, let's say, 10 mass, and you got good exposure on the patient. And you could tell that you got good exposure not by the image itself, but by your index number. So you used 80 kVp at 10 mass, you got a good index number, and you did not use a grid for whatever reason. And the doctor said, well, I want to see this again, but it's an ugly image. It's an ugly image because there's a lot of scatter on the image. I need you to go back and shoot this again with a grid. If you went back into the patient's room and you shot them with, let's say, an 8-to-1 grid, then your index number is going to show that you underexposed the patient. And the patient received the same dose, but the image receptor received less radiation because the transmitted X-rays were absorbed inside of the grid, those transmitted X-rays being both scatter and a little bit of unattenuated beam. So you underexpose the patient, or your image, your resulting image, the index number indicated underexposure. So how do we compensate for that? Well, what are we trying to accomplish with a grid? What is the purpose for a grid? We use a grid to clean up scatter radiation. So what technical factor controls how much scatter radiation we create? That would be KVP. So do we want to increase KVP and create more scatter radiation, or do we want to increase mass and clean up the same proportion of scatter that we would otherwise create anyway? And the answer is mass. We want to increase mass to compensate for grids. If we increase KVP, we increase scatter radiation. We increase scatter radiation, the grid has to work hard. And in fact, the grid will work harder to clean up as we increase KVP. It becomes more effective because we create more scatter radiation. It's got more scatter to clean up. So grid ratio, again, is the height of the grid strip, divided by the distance in between the grid strip. So height divided by this distance, not this distance. Grid frequency, though, is also a measure of grid ratio. And it's a measure of grid effectiveness, but it's a lot different. Frequency, just the name frequency, means how often something occurs. So grid frequency would be how often we have a grid strip. So it is taken into consideration in grid ratio, but it stands separate from grid ratio. And what I mean by that is, let's say we take this grid. If we take this grid, we got a grid ratio, a set grid ratio, and let's call this grid ratio 10 to 1. All right, and that's just a number I'm throwing out there. Don't try to calculate that based on this graphic, but let's say this is a 10 to 1. So the height divided by the distance in between is, gives us a grid ratio of 10 to 1. If I cut this grid in half, so that I cut it perfectly down the middle from left to right, then what I do is I reduce the height by half. So suddenly our grid ratio is now 5 to 1. All right. So we reduced our grid ratio because we reduced the height. But if I reintroduce the grid strips in between, so that I take this grid and I cut it in half, but somehow or another I mash it down in to where this upper portion of this grid strip is now here, then what I do is I reintroduce that lead. So what I did was increase my frequency. Frequency in this case would be 1, 2, 3, 4. When I cut this in half and I kind of recycled the grid and combined the two, then I would have 1, 2, 3, 4, 5, 6, 7, 8. So now I've got twice the number of grid strips. I cut the interspace material in half, and now I've got, again, a 10 to 1 grid because I doubled my frequency. So grid frequency all by itself only has to do with how frequent a grid strip, how often you see a grid strip in the interspace materials. So if I took this grid and I just added grid strips, this grid, we've got a frequency of 4. If I added grid strips, we'd have a grid frequency of 8. All right, so grid frequency, just how often they show up. Number of strips per centimeter. The thinner the strips, the fewer the grid lines. Okay, so back to our graphic. We shoot through this grid, and we're going to have absorption, and these grid strips are going to be very obvious. Your grid strips not going to be anywhere near this thick, but if they were, they'd be very, very obvious on the image. They would cast an artifact on the image. It's what we call grid lines because they are the lines of the grid. But if we could take this grid and make these strips, individual strips, half as thin but put twice as many in, then our grid ratio remains the same, but we've got thinner grid strips more often. So with the thinner grid strips more often, the grid strips themselves become less obvious. So since they're less obvious, then they're still made of lead. They're going to absorb most of the scatter radiation. You've thinned the hulls, so you've increased the effectiveness in that respect, but you've made them less obvious on the resultant image. Because the grid strips are thinner, they don't stand out quite as much, and as a result, you wind up with a cleaner looking image without the grid lines. So thinner strips, you have fewer grid lines, or the grid lines are less obvious. So if you have more strips, you have more lead. Increasing the number of strips without changing the strip width increases the grid ratio. And what I mean by that, again, is if we just add more grid strips in between each one of these, then we increase the grid ratio. If I cut this strip in half and I cut the distance in between also in half, then our grid ratio remains the same with the increased grid frequency. So increasing the number of strips without changing the strip width increases grid ratio. Higher ratio grids give us better cleanup. Unfortunately, we have higher patient exposure because we have to increase our mass in order to compensate for that. So again, the interspace material can be made of a number of different things. Aluminum is often used. It may help the grid lines to absorb scatter radiation, and it may help scatter radiation to be absorbed within the interspace material. The advantage is that it gives us less distinct grid lines, but unfortunately it does increase the patient dose. So the interspace material also becomes kind of like a grid strip, kind of like a beam attenuator. The benefit is that it does not absorb water. Some of the other materials will absorb some degree of moisture. Plastic fiber might, paper definitely will. And then you start to think about things like hydrostatic pressure. If you got a patient who's, I don't know, they've got a bleed, or if let's say they've got a bladder control issue, and you get some moisture in your grid, and your grid's got a crack in it, and the moisture gets into the crack, and you've got paper interspace material, hydrostatic pressure will push those grid lines apart and messes up your grid. So you don't have that problem with aluminum, less of a problem with plastic fiber than what you would with paper, but paper interspace materials are, I won't say they're abandoned, but they're used less frequently because of the problem with moisture. So technique compensation, we've got mass. Again, KVP creates scatter. So, the purpose for using a grid is to reduce the scatter radiation. And we want to not increase scatter radiation by using increased KVP. So we're going to use mass. Now, if you look at table 11-2 on page 197, you see approximate Bucky factor values for different types of grid ratios. So what a Bucky factor is the technique compensation for introduction of grid. So if you look on page 197, at the bottom right-hand corner, you see table 11-2. 11-2 shows you what your technique compensation would be. So if you're using a grid, or if you're not using a grid, your technique is times 1, which is just means that whatever technique you're using, that's the technique you're using. But if you introduce a 5-to-1 grid on a technique that you previously did not use a grid on, at 70 kVp, what you're going to have to do is adjust your mass by a factor of 2. If you're using an 8-to-1 grid, it's going to be a factor of 3. 12-to-1 grid, you're going to have to increase your mass by about 3.5. And a 16-to-1, you're going to have to increase your technique, your mass, by a factor of 4. So you got to increase your mass. The higher the grid ratio, the more scatter cleanup it has. But unfortunately, because of the increased lead content in the grid, you're going to have to adjust your mass to compensate. So that's hard on the X-ray tube, and it drives patient dose. Again, if you're using a 14-to-1 or 16-to-1 grid, you're going to use 4 times the radiation you would use without a grid. Radiation dose goes up significantly for a patient whenever we introduce a grid. All right, so grid performance. When we're talking about grid performance, we're talking about contrast improvement factor. And the contrast improvement factor is a mathematical formula to tell you how much better your contrast is with a grid versus without. So K represents contrast improvement factor. K equals contrast with divided by contrast without. And how you would get to the numbers for contrast with and contrast without would be off of your H&D curve. So you've got average gradient. Average gradient is the straight line portion of your H&D curve, and it is that rise over run that we talked about in a previous recording. So rise over run, if you have an average gradient of 1, or your contrast improvement factor rather of 1, then just like your average gradient, if it goes up basically at a 45-degree angle, with a contrast improvement factor of 1, you have no improvement at all. With a contrast improvement factor of greater than 1, then you've improved your contrast. So if you have a 1.5, then your contrast would be 0.5 better with a grid than what it was without it. So grid performance, as far as technical factor goes, your Bucky factor, your grid factor is what you use to determine how much of a technique change you're going to need when you introduce a grid, or if you change grid ratios from one to another. So the higher the Bucky factor, the more exposure to the patient. The higher the grid ratio, the higher the Bucky factor. Bucky factor increases with higher KVP. Again, I'd refer you to Table 11-2. Because you create more scatter radiation when you increase your KVP, there's more scatter available for the grid to absorb. So your Bucky factors are going to change. 5-to-1 grid at 90 kVp is going to absorb more scatter radiation than what it would at 70 kVp. So your Bucky factor has to increase. At 120 kVp is going to increase again. So your Bucky factor is going to change with the KVP that you utilize. So higher KVP means more scatter radiation. More scatter radiation created means more to absorb, and the more effective the grid becomes. For the test, though, what we're going to use is Bucky factors that look like this. For a 8-to-1, we're going to use 3. For 6-to-1, we're going to use 2. No grid, of course, is 1. And then we're going to combine a 10 and 12 at 4, and then a 16-to-1, we're going to use 5. So these are the Bucky factors that we'll use on the upcoming test that will be the week before the final. Fundamentally, there are 3 types of grids. There's some variations of each one, but there are mainly 3 types. The most common is what we call a focused grid. The crudest and really the easiest to use is what we call a parallel grid. And then we've got a crosshatch grid, which is either 2 parallel or 2 focused grids stacked on top of each other at right angles from each other, grid strips at right angles. So a parallel grid has all strips that are parallel, and you know the definition of parallel, meaning 2 things that go side by side and never touch. So a parallel grid is the easiest to manufacture. Pretty much all they have to do is stack the grid strips vertically and then sandwich the grid strip in between 2 pieces of interspace material. So they just alternate grid strip, interspace material, grid strip, interspace material. So they're all parallel to each other. They absorb radiation that's scattered across the short axis of the image receptor. That's providing that you've got rectangular image receptors like what we used to have in screens and films and in CR. If you're working on a DR system with a square image receptor, your grid hadn't changed, but your grid strips are going to be parallel to the long axis of the table. So it absorbs radiation across the short axis of the image receptor or across the lateral axis of the table or the wall bucky. That's important to note because you can angle with the length of the table. If the grid strips were going parallel to the short axis of the table, and if you tried to angle for, let's say, a town's view, then you're going to be angling against the grid strips and it's just not going to work. So all grids really, this is not unique to parallel grids. Parallel grids and focused grids, the grid strips travel with the long axis of the table, or they're vertical on a vertical bucky. So it's simplest to manufacture. The problem is you get more cutoff in the periphery. All right, so looking back over here, this is a parallel grid, graphic of a parallel grid. And you see the primary beam coming through. And they didn't put a patient on here because the patient's really pretty irrelevant for this particular graphic. But if you look at the remnant beam, or the beam that comes through the grid, what comes through directly under the middle of the central ray is pretty much what was before the central ray, except for where it was absorbed on this particular grid strip. So your hallways are completely filled up with X-ray beam. But because of the divergence of the central ray, you notice that the further out you go, the smaller the beam gets after the grid. So the grid strips absorb more X-rays because the hallways are not parallel to the grid strips as they are over here with a focus grid. So with a parallel grid, the further out you get in the periphery of the grid, the more grid cutoff you have. All of this cutoff X-ray beam is representative of grid cutoff. So you would see each one of these grid strips in a parallel grid, these less so than what you would these. So you get more cutoff in the periphery. So the strips are not parallel to the divergent central ray. So divergent central ray is coming down this way. If the grid strips were leaning in that way, then they would be parallel, but they're not. They're parallel to each other, but they are not parallel to the divergent central ray. And that's why we get grid cutoff in the periphery. It gets worse at short SID. So going back to this, if you can imagine backing your central ray up, then what you use is more of the center of the central ray. So grid cutoff in the periphery is less significant at increased SIDs, but if we were to drop our SID down to, let's say, this distance, then to cover this much of the grid, what we're going to have is much more divergence. So the more the beam diverges, the more cutoff you're going to have in the periphery. So it gets worse at decreased SID on a parallel grid. So the distance to grid cutoff is what we call SID over grid ratio, and that's the distance, the effectiveness of the grid. In both parallel and focus grid, you decrease your OID or your SID to a point where pretty much the center of the grid is the only portion where X-rays can go through, and the grid becomes fairly useless. It allows angling with the long axis of the grid. Again, that's not unique to a parallel grid. That applies to both parallel grid and a focus grid as well. So a crosshatched grid, or a cross-hatched grid, is usually two parallel grids together, and that's what you're looking at here is crosshatched. You got grid lines that are coming this way, that's a dark line, and grid lines that are going that way. So what the purpose for a crosshatched, or the effectiveness of a crosshatched, is that even on a parallel grid, if you have a patient here and your scatter radiation is coming off in this direction, then it cannot get through the grid, the interspace materials. But if the scatter radiation comes off and it goes in a direction that is either towards the head or the foot, but is still going parallel to these interspace materials, it can still get through very easily. But with a crosshatch grid, it's going to absorb in both dimensions, and X-rays, the scattered radiation, regardless of which direction it's going, cannot get through. So it absorbs X radiation scattered across the short and long axis of the image receptor, is much more effective than a parallel grid, has higher contrast improvement factor. All that sounds good, but you do get a higher radiation dose because it cleans up much more scattered radiation. So the radiation dose goes up. And the biggest problem is that you've got very little positioning latitude, and it allows for no central ray angulation, where the focus grid and the parallel grid you can angle in this dimension. With crosshatch you can't. So it's only perpendicular central ray. Patient dose goes up significantly, and you have very little positioning latitude. More on the positioning latitude here in a minute. The most common grid type in use today is a focused grid. And a focused grid is very difficult to manufacture. They're designed to minimize grid cutoff. Unfortunately, there's certain positioning errors that maximize grid cutoff with focused grid over a parallel grid. So the way that they are focused is the grid lines can't, C-A-N-T. It's not with an apostrophe like cannot, but it's can't. That means lean. They lean to coincide with the divergence of the beam. So they have to be used with specific SIDs. So going back to our graphic, if we were to take our tube and drop it down to where our divergence increases, then our divergent central ray is not going to be parallel to our grid strips. So it's got to be used with a specific SID. If you exceed the focus on a focused grid by either increasing too far or decreasing too close to the grid, then you're going to have grid cutoff in the periphery. Because the middle of the grid is essentially a parallel grid, you will not have grid cutoff here. If you exceed the focus, where you're going to have grid cutoff is in the periphery. So they have to be used with specific SIDs. So they have less positioning latitude than parallel, because if let's say you're doing a portable and you misposition the patient on the side, maybe they're not dead square in the middle of the grid, they misposition a little bit on the side, and you position directly above the patient rather than directly above the grid, then your divergent central ray is not going to be as parallel to the interspace materials as if they were in the center of the grid. Likewise, the grid focus for a parallel grid is infinite. That means you can use it at any distance. For a focus grid, you've got to stay within a specific focus, and those focuses are usually pretty broad. Like a focus grid, the focus for a focus grid may be from, let's say, 40 to 80 inches. Anything beyond 80 inches is too far. Anything below 40 inches may be too close. So whenever you're looking at a grid, the way that you can tell whether or not you're working with a focus grid is it has to state the focus, the effective SID that you can use to best use the grid before you start seeing a lot of grid cutoff. So if you have a focus crosshatch, then you combine the problems with a focus grid with a crosshatch. So with a crosshatch, you can't angle in any direction. With focus crosshatch, your positioning over the grid has to be spot on. It can't be off in any possible way. So regardless of what type of grid we're using, we're going to see the grid lines. You just can't get past it. You may have to use a magnifying glass if you're using a portable, because most of your portable grids they use a grid frequency and a thickness of grid that minimizes whether or not you can see the grid lines, but they're there. All right, so you may not be able to see them with the naked eye, but they are there, always present. In the X-ray table, what we utilize is a moving grid. So the moving grid, and you can actually hear this when you make an exposure, that scrubbing sound that may be coming from your table is the reciprocating action or the oscillating action of the grid. When you make an exposure, you know the basics of exposure and how breathing techniques work. Breathing techniques on a T-spine, we have the patient breathe so it blurs out the lung markings. We're using basically that understanding to blur out the grid lines in a moving grid. So it was developed by Hollis Potter in 1920, and we call it the Potter-Bucky diaphragm. And we move the grid during the exposure to blur out the grid lines. And they move in one of two ways. Reciprocating, we've talked about the law of reciprocity. Law of reciprocity means back and forth, or reciprocity means back and forth. So a reciprocating grid just moves in the short axis across the table back and forth like this. So if your table length is going up and down the slide, then the grid motion would be back and forth so that during the exposure the grid lines blur out. Oscillating grids, on the other hand, go in a circular motion like so. And it's not as dramatic as what I'm drawing here. It may be very subtle, but they move in a circular motion. And both of those, the purpose is just to eliminate the grid lines, blur out the grid lines. The problems with a moving grid, number one, is mechanical failure. And it's really not as big a problem as what it sounds like. Mechanical failure means that for whatever reason, your reciprocation or your oscillation has stopped. It just doesn't work anymore. So what you've got there is now you've got a stationary grid. You use stationary grid all the time on a portable anyway, so it's really not all that big of a deal. The only time it might be a problem is if you're utilizing a focus grid, and most of the time you're going to have a focus grid inside of your table. But if it comes to rest, the grid comes to rest off of the midline of the table, then you're going to have grid cutoff issues. So mechanical failure is one. Two is it increases the OID. Using the grid directly under the tabletop but above the bucky causes you to have to increase your OID. You don't do that. It's in the design of the table. There has to be room for the grid. There's got to be room for the grid to move as well. So there's a space there that naturally increases the OID. And if the motion of the grid is too significant, then it can move, usually not the patient, but usually it'll move the table itself. So if it moves the table, or more specifically the image receptor, you may introduce motion on the image receptor. So grid positioning problems. These could apply to grid positioning in the table, but most of the time these are portable issues. So if you have a grid, regardless of what type it is, if it's a focus grid, a crosshatch grid, or parallel grid, all of these in some form apply. All right, so if you have an off-level grid, off-level means tilted, regardless of whether you've got a tilted parallel grid, tilted crosshatch grid, or tilted focus grid. What you're going to have is your central ray is pretty much going to broadside your lead strips. So you're going to have significant grid cutoff all the way across your image. So it gets bad. It's bad. So let's say you're taking an X-ray on a patient, and you've got a patient on one of those soft air beds, and it's not fully inflated, and you slide a gridded cassette or a image receptor with a tape-on grid on top of the image receptor under the patient. And because the bed is soft, the grid and the image receptor at an angle, you're going to have grid cutoff. If you're working with a focus grid and you're not centered to the middle of the focus grid, you're going to have grid cutoff. In both of these cases, with a focus grid, it may be more significant on one side than what it is on the other. One that is very specific to, this is not a problem on a parallel grid, by the way. It's not even as much of a problem on a crosshatch that's parallel grid. Crosshatch focus grid, you got a disaster here. So a couple of things that are not a problem on parallel grids are this, and then you've got upside down grid. If you got a parallel grid and you accidentally put it on the front of the image receptor upside down, it's still a parallel grid. But if you take a focus grid and you put it upside down, now your divergent central ray is coming this way and your grid strips are going that way. And the only place that you're going to have adequate exposure is going to be directly in the center.